Hi everyone, we are back and we are going to get into our redox reactions. Oxidation, in this process, the element's going to lose valence electrons. Reduction, we are gaining electrons. So oxidation, you can see this material is losing electrons. In the reaction, it's giving them up. Whereas here, we are actually gaining electrons during reduction. So one of the biggest, or one of the ways we actually visualize, especially galvanic corrosion, electrochemical corrosion, is through an electrochemical cell. And our cell is going to have half-cell reactions. Now, the key thing in this diagram we're about to see is that our cathode, typically when you're attaching essentially terminals, your red terminal is typically your positive terminal, and we want to typically just put that red terminal, the positive terminal, on our cathode material because we want electrons to flow into the cathode. Thus, cathode is going to undergo reduction because it's gaining electrons. When we do that and we have a cell that has positive terminal, negative terminal, when electrons flow this way from negative to positive, that's a positive voltage. If they flow from positive to negative, that's a negative voltage. So typically, that's how you want to set up the cell. So cathode is going to undergo reduction. Anode will give up electrons. That is oxidation. So that's kind of the key language that we're going to use here. So forget about red and black terminals are meaningless. Really, it's just we know if I flow from negative to positive, that's positive voltage. Positive to negative, that's negative voltage. So that's kind of the key thing there in those redox reactions. So, and we can kind of see that here. Negative to positive, anode oxidation, cathode reduction. So we can, and if we're in standard conditions, our materials, whatever these two materials may be, they are connected electrically via, some type of wire and through a medium that can conduct electrons, so our electrolyte. At standard conditions, they're going to be immersed in a 1 molar solution containing their own ions. So, for example, if we have copper here and iron here, that will be our materials, and they'll be in basically a solution containing their own ions. So where will the electrons flow if we set up a system like this, copper and iron? Well, here's where we actually are going to have to go back to our periodic table and look at our electronegativity, just to get a sense. Because again, the material that wants to grab the electrons will be the more electronegative. So electronegativity, if we remember, where are you? Where's my good friend electronegativity? Electronegativity right here is 1.91. Excellent. So we are going to be going towards, let's go ahead. That's 1 point. Let's see. Let's look at our copper. So our copper is going to be, let's go ahead. Where is our copper? Copper electronegativity is 1.9. Our, what is it? Copper and iron, I think. Let's look back. Our iron electronegativity is 1.83. So our electrons should ostensibly flow from iron to copper. So if we set this up as our negative terminal and this is our positive terminal, copper is going to undergo reduction. That's our cathode. Iron is going to undergo oxidation, which is going to give up electrons. So we can actually write a half-cell reaction here. So what's going to happen is iron is going to go from iron to iron plus, or 2 plus 2e minus. It's going to give up electrons here. It's going to go to oxidation. The copper 2 plus ions in solution are going to bind with those 2 electrons from iron, and they're going to produce copper. So on the cathode side, we are going to electroplate. We're going to add materials here. Whereas in the copper, we are going to corrode because material's being lost on this side. So it'll get infinitesimally smaller. So that's another thing. On the cathode side, we are going to undergo electroplating. On the anode side, we're going to undergo oxidation. Or, corrosion. So we can also calculate at standard conditions the voltage, and our full cell reaction here would be adding these two reactions together. So the full cell reaction would be Fe plus Cu2 plus, because these and this will cancel out, goes to Cu plus Fe2 plus. That would be our full cell reaction. We can calculate this voltage, or the E naught of our cell, by doing our E naught of the positive terminal, actually, excuse me. Yep, actually, our positive terminal minus E of our negative terminal. And when we do that, so we can look at, so our positive terminal would be 0.34 minus 0.440. So our E naught of our cell at standard conditions for this particular reaction would be 0.780. And we can confirm that right here. And we got it. So there you go. And you can confirm that if we switched it, the sign would switch as well. So we've got it. Fantastic. Well, next time we can do another example with iron and zinc, and we'll see you then. Thanks. Bye.